not necessarily true that if the Moline series looks simple, like here's a simple one, that you can find matching a good basis to go along with it. You may have to multiply the numerator and denominator by some other polynomials to put it into a form where you can find a matching basis. All right, so that's background. Now, at the International Congress of Mathematicians in 1971 in Nice, Andrew Gleason gave a talk about weighted enumerators of self-dual codes. And one of his main examples is the theorem about type 2 codes, binary self-dual codes with all weights divisible by 4. If you work out the Moline series for this group of order 192 that I mentioned, it's 1 over 1 minus lambda to the 8th times 1 minus lambda to the 24. 8 and 24. Well, we know what to look for. We have the Hamming code of length 8 and the Golay code of length 24. And we can check that the weighted enumerators of those two codes are indeed algebraically independent. And that's enough. So that tells Gleason that the weighted enumerator of a type 2 code is an element of the free ring with two generators. The weighted enumerator of the Hamming code, which is x to the 8th plus 14x to the 4th plus y to the 8th, and the weighted enumerator of the Golay code, which is x to the 24 plus 759 times x to the 16th y to the 8th plus 2576 x to the 12th y to the 12th plus 759 times x to the 8th y to the 16th plus y to the 24th, which is a bit of a mess. So we don't have to use that. We can actually clean it up by subtracting the cube of the Hamming weighted enumerator. This has degree 8, cube it, you get degree 24. Subtract that from the weighted enumerator of the Golay code, take out a constant, and you get x to the 4th times y to the 4th times x to the 4th minus y to the 4th to the 4th. So we will say the ring, it's nicer to say this ring of invariance is generated by the weighted enumerators of Hamming and Golay, but we can actually work with the weighted enumerators of the Hamming and this polynomial here, which I'll call delta 24. If we'd been working with lattices, the weighted enumerators would become theta series of lattices. This would become the generating function for the Ramanujan numbers, the cusp form for the particular ring of modular forms. So almost everything I'm talking about can be lifted up into the space of quadratic forms and sphere packings. So this Gleason theorem is very powerful. Suppose we consider the quadratic residue code of length 48. So now we'd work with the prime 47 instead of 23. We know how to construct the code. The code turns out to be very good. It's a type 2 code. It's got weights divisible by 4, and it has minimum distance 12. Suppose we want to know what its weight enumerator is. Well, we can use Gleason's theorem. Gleason's theorem says this is a homogeneous polynomial of degree 48, but is very strongly constrained. It must be made up of pieces, a linear combination of the 6th power of Hamming, the cube of Hamming and times Golay, and the square of Golay. There are only 3 pieces. There are only 3 degrees of freedom in this weight enumerator. Whatever the weight enumerator is, we can write it as a linear combination of W8 to the 6th, W8 cubed times delta 24, and delta 24 squared. And if we know, by checking somehow that the weight distribution, the minimum weight is 12, then we know that when we expand this, it must begin with a coefficients of a 1, 0 times y to the 4th, 0 times y to the 8th, and then some number times y to the 12th. And that's enough to determine the weight enumerator.
So you only have to solve 3 equations?
Yes.
With the unknowns?
And you know it has to begin, yes, and they're triangular because of the fact that we chose one of degree 8 and one of degree 24. So it's very easy to solve this. And here are the coefficients you need, 84 and 246. And lo and behold, you get the weight enumerator of the code, and it tells you that there are 17296 code words of weight 12. And the Asmus-Madsen theorem, that I'm going to come to in a minute, will say that that's a 5 design, I think. So here's Gleason, Nice, 1970. He actually only looked at types 1, 2, and 3. He didn't bother with type 4, but Jesse McWilliams and Colin Mellors and I did that, but it's very easy to do. If anyone had asked him, he would have immediately said, yes, that's what they are. But here's the theorem. This characterizes the weight enumerators of self-dual codes whose weights are multiples of something. Type 1, there are 2 generators. In each case, it's a free ring with 2 generators. It's a reflection group. I shouldn't have said Cox-Lincoln diagram. But they've been classified. They're Ugars. This is an Ugar of order 16. It's a dihedral group of order 16. You have McWilliams, 1, -1, 1, 1, and you have weights divisible by 2, so you have diagonal 1, -1. And that generates a group of order 16. The Moline series is 1 over 1 minus lambda squared times 1 minus lambda to the 8th. The matching codes are the trivial code of length 2 and the Hamming code. And if you subtract the 4th power of x squared plus y squared from the Hamming weight enumerator, you get another cusp form. You get the polynomial x squared y squared times s squared minus y squared squared, which is easy to work with. Type 2 I've mentioned already. Type 3, you get 2 now ternary codes. I haven't mentioned ternary codes before, but we get a nice code of length 4, which is on the next transparency, called the Tetra Code, and we get the Golay ternary code of length 12, which is based on the prime 11 working mod 3. It's a quadratic residue code, but now we're working over the field of 3 elements instead of 2. And again, we have a kind of a cusp weight enumerator. And the 4th type is for the Hermitian inner product codes over the field of 4 elements using the Hermitian inner product. There are 2 generators, one of length 2 and one of length 6. And this one corresponds to a code we call the hexacode. And the hexacode, well, here they are, those 2 codes, the Tetra Code and the hexacode. The Tetra Code looks like this. It's the first code you write down if you're looking for a self-dual code over the field of 3 elements. 1, 1, 1, 0. That's obviously got inner product 0 with itself. 1 plus 1 plus 1 is 0 mod 3. And you want something perpendicular to that. Well, how about 0, 1, 2, 1? I could have taken 0, 1, 2, 2, but 0, 1, 2, 1 is sort of nicer. So those 2 vectors of length 4 over the field of 3 elements generate the Tetra Code. It's got minimum distance 3, it's a single error correcting code, minimal Hamming distance 3. And the weight enumerator is x to the 4th plus 8 xy cubed. It's got 9 code words in total, right? 3 squared, and the 0 code word and 8 code words of Hamming weight 3. And its group is twice S4. You must have a 2 because you can it's a linear code over GF3. So you can multiply by 1 or minus 1. And likewise, in GF4, we can multiply by all of the 3 units, so we get a scalar factor of 3. So this is the Tetra Code. The hexacode is a code of length 6 over the field of 4 elements. We take GF4 to be the field of 2 elements when we adjoin a cube root of unity, as usual. We take a primitively reducible polynomial, x squared plus x plus 1, adjoin the root, add it to F2, and we get a field of 4 elements. We have conjugation, which is mapping omega to omega squared, and so the Hermitian inner product is you take the sum of AI, BI bar, where the barring means you square the elements. So a generator matrix for this looks like this. 1 naught naught, 1 omega omega, and so on. It's got weight enumerator x to the 6 plus 45x squared y to the 4th plus 18y to the 6. It's got the alternating group acting on the coordinates, whereas this only had the symmetric. I mean, this had more. Here you could permute all the coordinates freely. There you can only take even permutations of the coordinates. and this has dimension 3.
Wait, can I ask, what's the weight of omega? Did you mention?
1.
One.
I'm sorry. Yes, I should have said it. We could have taken it to be anything, but I'm working here with Hamming weights.
Okay.
So Hamming is just 1 if it's non-zero,
Okay.
and 0 if it's 0. Yes. Yeah, in a minute when I get to codes over the integers mod 4, then we use a different weighting system. So yeah, good question. So because Gleason's theorem tells us that these weight enumerators satisfy very strong constraints, you don't have much freedom in getting the minimum distance to be large. Like in that code of length 48 I showed you, I had 3 coefficients I could pick. So we have to make the coefficient of x to the n has to be 1. And then if we want to get a high minimum distance, the next coefficients we take to be 0. But there are very few coefficients. We have very few degrees of freedom. If we're looking at a code of length a code of length n over GF2, a type 2 code, we have n over 20, the floor of n over 24 plus 1 degrees of freedom. We had 3 degrees of freedom for a code of length 48. So in general, and each degree of freedom picks up a minimum distance of 4. So it's not completely trivial to prove this, but you get an upper bound. No, this part is trivial. It's when you do it for lattices. It's much less trivial. But anyway, using this theorem, using Gleason's theorem, you can prove that an upper bound on the minimum distance of these 4 types of self-dual codes, which is something that Colin Mellors and I did a long time ago. And then with Andrew Lishko, we looked at what things can meet, how many times can you meet these bounds. And so we know quite a lot about codes that meet the bounds. And in general, there are only finitely many. And when you do it for lattices, it gets more interesting. And you show that there are not infinitely many lattices as good as the Leech lattice, for instance. There are not infinitely many codes like the Golay code. You can't get such good codes because of this restriction, because of the theorem. There's a theorem. I don't like this theorem very much. It's a bit messy. But it tells you that if certain conditions are satisfied, the code words of each weight form a t-design for some value of t. So just here's the fine print. If we apply it to the Golay code, it says the Golay code has weights 0, 8, 12, 16, and 24. You apply the theorem, this is Asmus and Matson in 1969, we can apply the theorem with t equals 5, and it tells us that the code words of each weight form a t-design. And in particular, if we look at the code words of weight 8 in the Hamming code, they form a Steiner system. Steiner system means there's a unique block through any 5 points. But a t-design, in general, it has to be a constant number of blocks through any 5 points. That's the parameter lambda. Here the lambda is 1 for the 5 design. Yeah, and these are the octets, as I mentioned. And these underlie what's called the miracle octet generator, which is what you need to learn if you're going to do calculations with the Leech lattice. And C splag, I bought with Conway for much more about that. Yeah, all right, 5 more minutes. Z4 appears. So, classical coding theory was codes over fields. And there's a nice story. In the mid-1960s, John Robinson, from somewhere in the Midwest, was looking at optimal codes. And he noticed, if you do the sphere packing bound for double error correcting codes of length 15, if you want a binary code of length 15 that can correct 2 errors, what's the most code words you can have? The sphere packing bound says you could conceivably have 256 code words. It wasn't 289 or 213, which would be kind of ugly. 256, 2 to the 8th. Beautiful. Does this code exist? So he gave a talk somewhere in Long Island, and a high school student called Nordstrom was there, and he went away and ran a computer and found an example of this code. So it became known as the Nordstrom-Robinson code. It's a code of length 15, minimum distance 5. If you add an overall parity check, it becomes a code of length 16 with minimum distance 6 and with 256 code words. And it's not linear. You can prove there's no linear code of length 15 or 16 with these properties. But the length 16 code has this fantastic property that it's fixed. If you look at the weight enumerator, it's the same with respect to every code word. Even though it's not linear, whatever code word you're sitting at, you look out and you see 112 code words at distance 6 from you. You see 30 code words at distance 8 from you. The weight enumerator is invariant of where you're sitting. And it looks like it behaves like it's the weight enumerator of a linear code. It satisfies the McWilliams identity. It's fixed under the McWilliams transformation. But it's not linear. The weight enumerator is 1, 0, 112, 30, 112, 0, 0, 1. And you can get it. We worked quite hard on this after it was discovered. And we found you can get it by taking the Hamming code of length 16, a Reed-Muller code of length 16, and taking 7 cosets of it in a non-linear way. But many years later, we discovered that in fact, it's really a self-dual code over the ring, not over the field, but over the Galois ring, Z mod 4Z, of length 8. And so you can take this code, which is easy to construct, it's on the next slide, and you can map it to a binary code. You get the nonlinear. So it's linear over Z mod 4Z. This is a code I already knew about. In fact, that's how I discovered it. It comes up in looking at one of the Niemeyer lattices in 24 dimensions. It's one of the 23 Niemeyer unimodular lattices in 24 dimensions. It's the Octave Code. It's a code of length 8 over Z mod 4Z. It's got 4 to the 4th code words. It's linear now. And if you map, here's its weight enumerator. I'm looking at the particular weight enumerator now, where I keep track separately of zeros, plus or minus 1s, and 2s. And 2 here gets weight 2. Plus or minus 1s get weight 1, and so that's the weight enumerator. If you map it to a binary code using the obvious gray map, you map 0 to 0, 0, 1 to 0, 1, 2 to 1, 1, and 3 to 1, 0, you get the Nordstrom-Robinson code. Well, so that, and we have a Gleason Theorem for it. And so, in 1998, Eric Rains and I wrote a very long chapter in the Handbook of Coding Theory. Originally, there were 4 types of self-dual codes. We increased it to 9 types, because in the meantime, other people had looked at other rings. And so we had 9 families of types. And each one, there was an individual, they had to be treated separately, and we came up with the Gleason Theorem. So then a few years went by, and Eric Rains and Gabriela Neba and I wrote our book on self-dual codes. And the idea was to give a general definition of type, which includes all the types that people had looked at. People had done many, many special cases. And the idea is that you come up with a general kind of Gleason theorem. It says, if you're looking at the weight enumerators belong to the invariant ring. They're invariant under a certain group, from a particular class of group. And furthermore, the ring of invariance is always spanned by weight enumerators of that type. So this included many of the theorems that various various people had discovered about various kinds of rings. And so it's very powerful. And there's the book. And for the classical theory, I refer you to my book with Jesse. So I will stop there.
Is there any question?
So these nonlinear codes are codes over the other rings? over the rings.
Yes, they're linear over the rings, exactly, but not over the field. They're not over a field. Yeah, non-linear over the field.
They're sort of linear.
They're sort of, yeah, I mean, they really are linear once you look at it with the right kind of glasses. I should say, one of the unsolved problems is we've now got many kinds of rings, of self-dual codes over rings. We don't have enough good examples like the Hamming code and the Golay code. There are a lot of rings you could look at. If you want a nice project, look at some self-dual codes over matrix rings or rings with strange properties, or not so strange, and find nice examples.
Well, now you're passing to non-commutative rings. Over
Yeah.
matrix rings.
Yeah, sure. That matrix rings. Yeah, definitely. That comes up in looking at multiple weight enumerators, higher genus weight enumerators. That comes up naturally.
Have people tried to do to find such codes with more complicated things?
Not really, no. No. And the Moline series gives you a hint of where to look. Because like the Moline series for type 2 codes, you've got the numbers 8 and 24. The trouble is, for these bigger rings, the Moline series tend to get very messy. You have potentially, I mean, we have examples where there are millions of terms in the numerator, you know, and a product of 4 terms in the denominator. But literally millions in the numerator. So it's impossible to give a good description, as far as I know, of the rings of invariance that come up in these general cases.
What's nice about dual codes in terms of, I guess, error correcting? Is there anything particularly nice about them?
Yeah, you can. They have nice decoding algorithms because because of all the symmetry in the coordinates. If you have a 5 transitive group acting, it simplifies the decoding a lot.
So to get pictures from Mars, they use.
I think they use Reed. Well, I don't know what they're using now. They were using Reed-Muller codes.
And that's all. Yeah.
So on the lattice level, what would be the analog of working over these non-field rings? What's your view of that?
Yeah, I'm not sure. I don't really know.
A historical question. What happened to the high school student Nordstrom? Did they become PhD?
Never heard from him again.
Okay, let's thank Professor Sloane again.